Every single bridge you've ever walked across, driven over, or photographed is broken. Not damaged, not faulty, intentionally, deliberately engineered to be broken. And if engineers ever decided to fix that, to seal every bridge up perfectly, completely, with no gaps whatsoever, the bridge would destroy itself. Look closely at any large bridge. Run your eyes along the edge where the road meets the structure. You'll see them, these strange, jagged, comb-like metal teeth, interlocking with each other like two hairbrushes pressed face to face. They look almost industrial, almost aggressive, like the bridge is biting into itself. Most people walk right over them without a second thought, but those teeth are one of the most quietly brilliant engineering solutions in the history of construction. They are the reason bridges don't crack in half during summer. They are the reason the road feels smooth under your tires instead of like a series of violent jolts. And they are the reason that the Golden Gate Bridge, which carries roughly 112,000 vehicles every single day, is still standing. These are called expansion joints, and the story behind them goes all the way down to the fundamental nature of matter itself. Everything expands when it gets hot. Everything. Your coffee mug, the air in your lungs, the steel cables holding up a suspension bridge. This isn't a quirk of engineering or a material defect. It's basic physics. When atoms get hot, they vibrate faster. They push against each other harder, and the entire material they form gets slightly larger. And when things cool down, the atoms slow down, pull inward, and the material contracts. For small objects, this barely matters. Your car key is slightly bigger in July than it is in January, but not in any way you'd ever notice. But now scale that up. Take a bridge. A real bridge, say something like the Oresund Bridge connecting Denmark and Sweden, stretching nearly 8 kilometers across open water. That bridge is made of tens of thousands of tons of steel and concrete. And that steel, on a hot summer day versus a cold winter night, it can expand or contract by nearly half a meter, 50 centimeters. We're talking about a bridge that literally changes its own length depending on the weather. If that bridge were one sealed, rigid, uninterrupted piece of material, no gaps, no flexibility, no room to move, the forces generated by that thermal expansion would have nowhere to go. And physics doesn't negotiate. That energy would have to go somewhere, so it would go into the structure itself. Think about it this way. Hold a wooden ruler with both hands and try to bend it. Feel the resistance? Now imagine you're not a person bending a ruler, but the sun heating up half a kilometer of structural steel. The force we're talking about is incomprehensible. Steel under that kind of thermal stress can buckle, warp, and fracture. Concrete, which handles compression beautifully but hates being pulled or twisted, will crack. And a crack in a bridge deck isn't just an aesthetic problem. It's the beginning of structural failure. So engineers from the very earliest days of large-scale bridge building understood that you cannot fight this force. You have to accommodate it. You have to give the bridge room to breathe. And that's exactly what expansion joints do. They are the breathing room. The concept has been around longer than most people realize. In the 1800s, when cast iron and wrought iron railway bridges were being built across Europe and North America, engineers noticed that during extreme temperature changes, bridges would emit loud cracking and groaning sounds. Some would develop visible deformations. A few failed catastrophically. The engineering community realized that bridges needed deliberate gaps, spaces built into the structure that would close up when the material expanded and open up when it contracted. Simple in theory. But in practice, you can't just leave an open hole in a road that thousands of cars drive over every day. This is where the teeth come in. The interlocking finger design, that comb-like pattern you see, solves a problem that seems almost paradoxical at first. You need a gap that can open and close, but you also need a surface that vehicles can drive across smoothly. How do you have both? The fingers, or combs, solve this elegantly. Each side of the joint has a series of long, rectangular metal projections, the teeth. They interlock with the teeth on the opposite side, like two combs sliding into each other. When the bridge expands in summer heat, the teeth slide together, overlapping more. When the bridge contracts in winter cold, the teeth slide apart, the gap between them widens. But at all times, the interlocking fingers provide a continuous load-bearing surface. A car tire rolling over the joint at highway speed doesn't fall into a hole. It rolls across a series of small, manageable gaps between the teeth, each gap too narrow to swallow a tire, but wide enough collectively to allow the entire joint to move. That sound you sometimes hear when you drive over a bridge and there's a distinct thunk or rhythmic bumping, that's your tires rolling over the expansion joint. You've been experiencing this engineering marvel your entire life without knowing what it was. Now, the forces that expansion joints manage aren't just from temperature, and this is where it gets even more interesting. Bridges move constantly. Under load, when 100 cars and trucks are on the deck simultaneously, the bridge deflects slightly downward. When the load clears, it springs back. This happens thousands of times a day. The bridge also sways in wind. Suspension bridges especially are designed to be flexible, swaying several feet in strong storms. A rigid bridge in high wind is like a rigid tree in a hurricane. It snaps. A flexible bridge, like a willow, bends and survives. And then there are earthquakes. In seismically active zones, expansion joints have to accommodate not just gentle thermal expansion, but violent, sudden ground movement. The joints at the Bay Bridge in San Francisco are engineered to handle the deck shifting several inches in a matter of seconds. During the 1989 Loma Prieta earthquake, sections of the Bay Bridge actually failed, but the expansion joints in the main structure performed largely as designed, absorbing movement that would otherwise have propagated as catastrophic fractures through the entire deck. The engineering of a modern expansion joint is genuinely sophisticated. High-traffic highway bridges use what's called a modular expansion joint, essentially multiple sets of interlocking combs arranged in parallel, each one separated by a sealed rubber strip. These rubber strips, called seals, serve a second critical purpose. They prevent water, road salt, and debris from falling through the joint and corroding the structural steel below. Because here's something that often gets overlooked. The threat to a bridge isn't just the forces acting on it. It's chemistry. Water and salt are extraordinarily corrosive to steel. If expansion joints weren't sealed, every rainstorm would send corrosive water cascading directly onto the bridge's structural components below the deck. The expansion joint, by providing a weatherproof seal that still allows movement, is simultaneously solving a structural problem and a chemical one. The seals themselves are a feat of materials engineering. They need to be flexible enough to compress and stretch repeatedly without cracking, potentially millions of times over the bridge's lifespan. They need to resist UV degradation from decades of sunlight. They need to maintain their sealing properties in temperatures that might range from well below freezing to intense summer heat. Modern expansion joint seals are typically made from neoprene or specialized polymer compounds, engineered to specific tolerances for each bridge's expected range of movement. And that expected range of movement is precisely calculated. Engineers don't just guess how much a bridge will expand. They calculate it using the coefficient of thermal expansion of the specific materials used, steel, concrete, or composite combinations, multiplied by the temperature range the bridge will experience across its entire design life, multiplied by the length of each bridge segment. For a long steel bridge in a climate with significant seasonal variation, that calculation might yield a required joint movement range of several inches. For a shorter concrete bridge in a mild climate, it might be less than an inch. Every joint is custom engineered to the specific bridge. Some of the world's most dramatic expansion joints are on the longest bridges. The Akashi Kaikyo Bridge in Japan, the longest suspension bridge in the world, with a main span of nearly 2 kilometers, has expansion joints that must handle extraordinary movement. The bridge's deck can sway significantly in the typhoons that regularly pass through the region, and the thermal expansion of cables and deck across that span is substantial. The engineering required to keep that bridge functional across decades of such movement is a continuous, ongoing calculation. And speaking of long-term, expansion joints don't last forever. They are considered wearing parts of a bridge, similar in concept to how brake pads wear out on a car. The rubber seals degrade, the metal fingers can wear at their contact surfaces. Joints need to be inspected regularly and replaced on a maintenance cycle. This is why bridge maintenance budgets always include expansion joint replacement. It's not a repair, it's a scheduled renewal of a component designed to wear, so the rest of the bridge doesn't have to. When expansion joints fail, or are absent, improperly installed, or blocked with debris, the results can be dramatic. Blocked joints can't close properly as the bridge expands, and the force has to go somewhere. There are documented cases of expansion joints packed with incompressible debris, stones, hardened dirt, compacted grit, that prevented the joint from functioning. The expanding bridge, finding no room in the joint, pushes against adjacent structures. Concrete cracks, abutments shift. Approach roads get lifted. The damage is expensive, sometimes structurally significant, and entirely preventable with routine maintenance. This is actually why bridge inspection is so methodical, and why expansion joints are one of the first things inspectors check. A properly functioning expansion joint is invisible to drivers. Everything feels smooth, the bridge works. A failing joint announces itself through noise, through rough driving, through visible damage. But by the time it's visible, the damage is already done. The Romans built some extraordinary structures, and their engineers understood empirically that large structures needed to accommodate movement. They used flexible lime mortars rather than rigid modern cements, which gave their masonry the slight flexibility to survive centuries of thermal cycling. But the deliberate, precision-engineered expansion joint as we know it today is a product of the industrial age, refined through the 19th and 20th centuries as bridges got longer, faster vehicles put more dynamic load on them, and our understanding of material science deepened. Today, there are bridges where expansion joints are so large and so complex that they look like pieces of industrial machinery inserted into the road. Some modular joints for very long bridges have dozens of individual combs and seals spanning gaps of a foot or more. They move constantly, silently, invisibly, thousands of times a day. Every time a truck rolls over them, every time the temperature drops 10 degrees, every time the wind picks up. The next time you cross a bridge, listen for that sound, that rhythm of tires crossing the joints. It's not an imperfection. It's the bridge doing exactly what it was designed to do. It's the bridge breathing. And here's the fact that tends to stop people cold when they hear it. The Eiffel Tower, not a bridge, but made of iron, and subject to the same physics, grows by roughly 15 centimeters in summer compared to winter. Every year, the Eiffel Tower gets taller in July than it is in January. The thermal expansion of iron across its full height in the Parisian climate produces that much change in its dimensions. If the Eiffel Tower were made of a single, perfectly rigid material with no capacity to accommodate that movement, the thermal stresses would crack it apart within a few decades. Every massive structure you've ever admired, every bridge, every tower, every long rail line, every runway, is quietly, constantly moving. The gaps you see aren't flaws. They're the spaces that make permanence possible.